Welcome guys. So today we'll be looking at linear transformation on matrices. And just before we do this, as usual, what I'd like you to do is just pause the video and have a go at this 3 question. So when we work out AB, we'll get the following matrix, and BA is this. So as we've seen in the last video, AB is not necessarily the same as BA, and the matrix multiplication, they most often are different. And here's the answer for question 2 and 3. So you'll be familiar with transformation from GCSE, so things like reflection, rotation, translation, enlargement. So we're going to look at it with matrices. So it's effectively transformation, but using a linear set of matrices. So transformation moves all points x, y in a plane according to same rule. So the new points are known as the image. The 3 transformations, S, T, and U, are defined below. Find the image of the point 2, 3 under each of this transformation. So if we take first one, S, so we see xy coordinate has been changed into x plus 4 and y minus 1. You can write the coordinate as a vector, i.e. the direction from the origin, and substitute the values. So the coordinate 2, 3 has now become 2 plus 4 and 3 minus 1. So under that transformation, S, the image is now 6, 2. So you guys pause the video and work out T and U. Okay, so for T, if we follow this transformation, same as before, if we take our coordinates, 2, 3, substitute it in, and we do calculation, we'll see our coordinate now becomes 1, 5 under that transformation. Now let's look at U. So we're going to calculate by substituting in 2, 3, and that gives us 6 minus 4, so coordinate 6 minus 4. A linear transformation has 2 properties. It only involves a linear transformations of x and y, so no powers. The origin is not moved by the transformation. So only S involves a linear transformation, the origin is not moved. Let's look at T. Only involves linear transformation, the origin is not moved. U only involves linear transformation, the origin is not moved. So you could see which one with a tick. Tick means it meets the criteria, and cross obviously means it doesn't meet the criteria. So in this case, T is the only linear transformation here. So the linear transformation S, which transforms xy with ax plus by cx plus dy, can be represented by the matrix A, B, C, D, and we call the matrix M. Since if you have the matrix A, B, C, D times with xy, like we looked at in the previous lesson, you get the following. Remember, you do row times column. So A times X plus B times Y for the first element. For the second element, C times X plus D times Y. Find matrices to represent these linear transformations. So pause the video and you have a go at this. So we've got T and V. So if we start off with T, write in the form shown to the right, or in this case to the left, with this matrix X. So we could just simply write this as 1, 2, 3, 0 elements. So for V, write it the form as S. So we could just take the, if we look at the coefficients here, because there's no 0, we could say that's 0x. So we could just write this as 0, minus 2, and 3, and 1. So your new vertice is 1, 3, minus 1, 7, 3, 9, and 5, 5. So you can use matrices to describe linear transformations. So if we look at the original vertices again, okay, and we look at the new vertices, so you could visualize what's going on now. So we're going to be looking at how to represent reflections, rotations, and enlargement using matrices. So translations are not linear transformations, as the origin would move. So this will not be covered here. To decide what transformation a matrix performs, you should consider its effect on two simple vectors. You can also think of them as coordinates. So we go 1, 0, 0, 1. As matrix, we could represent these coordinates as 1, 0, and 0, 1, like this. So describe fully the geometrical transformation represented by this matrix. This is telling us if the original coordinates are 1, 0, and 0, 1, the new coordinates will be 3, 0, and 0, 3. And it's important that they are in correct order. So you should always start with a sketch of 1, 0, 0, 1, and then mark on the two new coordinates. So remember, it's just a sketch, so we could do something like this: 1, 0, 0, 1, and then look at the new coordinates 3, 0, and 0, 3. After this, consider what transformation has happened. The coordinates have stretched outwards. The matrix is an enlargement of a scale factor 3 with center 0, 0. Describe fully the geometrical transformation represented by this matrix. So this is telling us if the original coordinates are 1, 0, and 0, 1, the new coordinates will be minus 1, 0, and 0, 1. Sorry, 0, minus 1. So same as before, make sure you write this in correct order. So we should always start off by sketching the 1, 0, 0, 1, the unit matrix. And now we could start plotting the other one, minus 1, 0, and 0, minus 1. So after this, we could consider the transformation. And here you need to be careful. This is not a reflection in the y equal to x line, as coordinates would not match up. Both have moved or rotated 180 degrees around the center. So therefore, we'll describe the transformation as a rotation of 180 degrees around the origin. And remember, for 180 degrees, we don't need to say clockwise or anti-clockwise. So let's have a look at this one. We're going to describe the transformation 0, minus 1, minus 1, 0. So again, this is telling us the original matrix 1, 0, 0, 1. And the new coordinates are 0, minus 1, and minus 1, 0. So same as before, we start off by sketching 1, 0, and 0, 1. and then we'll sketch the new one, which is 0, -1, and -1, 0. And this all been color coded here for you. So after this, we're going to consider the transformation. So a bit like last time, this is not a reflection in the line y equal to x, as the coordinate does not match up. If you look at the coordinate 1, 0, and this is 0, 1. So this is clearly not a reflection. However, they have been reflected in a different way. So it's not a reflection on y equal to x. If you look at the reflection on y equal to -x, you can see the coordinates, they match up. So therefore the transformation is a reflection in the line y equal to -x. So you can use matrices to represent rotations, reflections, and enlargement. We'll consider these problems in reverse, finding a matrix of a particular transformation. As you have seen, quick sketches are vital when thinking about these kind of problems. So find a matrix to represent the transformation, reflection in the y-axis. So we start off with a sketch as normal. So we've got 1, 0, 0, 1. And the reflection in the y-axis will move 1, 0 coordinate across. So the original pair 1, 0, 0, 1 will now just be -1, 0, 0, 1. So this matrix will perform a reflection in the y-axis. So let's have a look at this. The enlargement with center 0, 0 and a scale factor of 2. So we start off with a sketch. So we've got scale factor of 2, so it's going to be twice as big. So 2, 0 that way and 0, 2 here. So if we look at the original pair 1, 0, 0, 1, we can just replace the coordinates. So with 2, 0 and 0, 2. This matrix will enlarge the shape by a scale factor of 2 at the origin. Okay, so now we have the values here of the opposite and adjacent. We could also just work that out by intuition. So it's just on this side here on the left hand side, so we'll have -1 over √2, and the height is still the same, so it's 1 over √2. So now you could adjust the transformation matrix based on the new coordinates. So the coordinate 1, 0, 0, 1, we just replace it with 1 over √2, 1 over √2, and then -1 over √2 and 1 over √2. So this matrix will rotate the shape 45 degrees anti-clockwise about 0, 0. So as a general rule, for rotation of angle theta anti-clockwise about the origin is given with this: cos theta sine theta minus sine theta cos theta. There are also two definitions you should remember: invariant points. So these are points which map onto themselves under the transformation, and invariant lines. So these are the lines which map onto themselves under the transformation.